Hey, what's going on, guys? Today we are gonna talk about another topic in descriptive statistics, which is measure of dispersion. All right. So in this section, we will basically try to measure how much we diverge from the mean. All right. So let's see. Here's the outline. First of all, let's look at why we need to define these measurements, these scalar values. And then one of them is actually the first one is going to be the range of a data set. We will see that. And the most important one, of course, standard deviation, which I assume you heard about it before. Okay, so because that's one of the most common statistical measurements. Okay, and the last one is the coefficient of variation, which is a nice way to compare different data sets. Okay. Now here's the motivation. Assume that we have two different data sets. In X we have numbers which are accumulated around 25, and in Y we have numbers which are more spread out than X. Okay, so we can see that we have 1, 2, 3 here, and then suddenly we jump to 47, 48, etc. Okay, so both of them have the same mean, 25. Okay, so you can compute them. So what this means is, guys, if we try to interpret these data sets just looking at 25, so we will probably fail to give a meaningful interpretation. Why? Because the mean of both of them are same, 25, but y is more spread out than x. So that means um, we cannot make an inference about this property, okay, about this property using mean. All right, so we need to come up with different ways to do it. So that's the motivation. All right. So let's look at the first one. So what we can do is, well, look at these data sets. So the smallest value is 24, the largest one is 26. So we can look at the difference. We can look at the difference here, which is 2, and we can look at the difference here again with the maximum and the minimum. It's gonna be 48. Then we can try to interpret the data using that measurement, what we call range of a data set. Here's the definition. So the range of a data set is the difference between the largest and the smallest values in our data set. Okay, so for example, there are some people here, some workers here, and their salaries listed in the table. So what is the range in this case? Range is gonna be the maximum salary, which is 210,000, and the minimum salary, which is 115,000. Okay, so the difference is gonna be 95,000. So this is our range. So the question is, can we use the range of a data set in a broader sense? The answer is no. And we can easily see why, because the range is greatly influenced by the outliers. For example, let's change the minimum salary to 50,000, then see what will happen. If you change it to minimum salary to 50,000, then the range is gonna be 160,000. So it will quickly jump from 95,000 to 160,000. So that means it's influenced by single smallest or largest numbers. Okay, so that's why that's not a good way to interpret a data set. So the most common one, guys, is standard deviation. So let's see what it is. First of all, let's define what we mean by deviation. So we have a data set, and the point in that data set, let's say a value, and we know the mean, and the difference is gonna be the deviation of that point from the mean. Okay, so easy enough. So for example, let's take this data set. So there are 5 values here, and the mean is 17. You can compute that. And if you look at the deviations, guys, we have some minus values and some plus values, some positive values, some negative values, and some positive values. So if we are to find the total deviation using this idea, we will find it's 0. So is it reasonable? What do you think? I don't think so, because deviation is not 0 for this data set. See, because the mean is 17 and we have some values spread around 17. Okay, so the deviation is not 0. We have a value which is smaller than 17, and we have a value greater than 17. So deviation should be something which is different than 0. So how can we fix this problem? The problem is obvious, right? We have minus values and plus values, so they cancel each other. So idea is make them positive. So how do we do that? So square them, all right? So once we find the deviation, we square each number here. So then it's going to give us positive values, all right? So then what we can do is, so we can sum those deviations, all right? We can sum those deviations, but it's going to be a huge number, all right? And that number is not a way to is not a good way to interpret this data set. So then we can average them out like this. So first of all, find the sum of all deviations, then divide by, normally we would divide by 5, which is the number of data points in our data set. But just for now, let's skip the detail because this is very theoretical. So instead of dividing by 5, we divide by 4, okay, one less. So we are gonna find 19. So it's okay, we can take this number, 19, and we can try to interpret the deviation of this data set with 19. But what is the problem? There's a problem, there's a small problem here. Let's say if these values, I mean the original values, are given in terms of inch, for example, then that 19, that result would be inch square, because we square those values and then we divide by a scalar. So still, so this is gonna be square here, 19 square inch. So we don't like it because we want to find the result which is compatible with the original unit. So how do we do that? So at the first we square, and at the last we are gonna take the square root. Okay, so and then when we take the square root, the result is gonna be 4.36. Okay, so here's the definition of standard deviation based on that example. First of all, we look at the difference between the data point and the mean. Then we square them. We square this value and we sum over all data points. Then divide by n minus 1 and take the square root. Okay, so that's the idea. So we can compute standard deviation using by following 4 steps. First of all, of course, we need the mean. We compute the mean, and then we look at the difference between individual data point and the mean and square it, and do it for each data values. Then add them up, divide by n minus 1. Meanwhile, this quantity here, guys, the quantity that we take the square root of is called the variance. Okay, it's another important measurement in statistics. So this is variance. Then take the square root of variance. So let's look at an example. Here we have ticket prices. So what are they? So you are planning a holiday, summer holiday, and you are listing some of the prices from your location to your destination. Okay, and then here are the prices. Now the question is, what is the standard deviation of this data set and how can we interpret the result? So first of all, let's find the result. So the mean is 210. Then let's make a chart to find those square deviations, square of the deviations. Here is the data points. These are the deviations, and once we find the deviation, we can square it to make it positive. All right, and then take the average, of course, using 6 minus 1, not 6. Okay, and the average is gonna be 68.8. Then the last step, step 4, take the square root. We are gonna find 8. Now, the standard deviation is $8, guys, $8.2. So how can we interpret that? So, look at the mean. So the mean of this data set is 210, okay, and the standard deviation is 8. So we interpret this result as follows. So since 8 is a small number, is a relatively small number, is actually a very small number, comparing to 210, that means the ticket prices are not that much different from each other. And that's true, alright? So standard deviation is low. That means ticket prices, we can expect ticket prices to be very close to each other. And that's true. Look at the ticket prices. The maximum one is 219, okay? And the minimum one is 195, okay? So they are not that much different from each other, okay? So that's how we interpret the standard deviation. For example, what do you think about the following case? What if our standard deviation was to be 0? Okay, how do we interpret that? So see, if our standard deviation is 0, guys, that means all these values are same. Okay, all of these values should be same. All right. So then, because look at that, for example, if they are all same, then when we take the average, okay, if they are all same, when we take the average is gonna be same for the individual values. So that means deviations are gonna be 0. All of them are gonna be 0. That's why standard deviation is gonna be 0 at the end. Okay. So in the previous section, we have seen the frequency distribution of a given dataset. Now let's see, when we are given a frequency distribution, how we can compute standard deviation. So it's very similar, definition is very similar. So standard deviation of a frequency distribution will look like this, okay? So the idea is, once we find the square deviations here, once we find the square deviations, we are going to multiply by the corresponding frequency of data point, of that data point, okay? Here f is the frequency of that data point x, okay? So here's the example. So assume that we are considering investing in a software company, and then we are looking at the closing prices in the stock market for the past 20 trading sessions. Okay, so we look at the closing prices to see how stable it is. Okay, so that's a small information. Now here's the closing prices. For example, when we look at these past 20 trading sessions, that means there are 20. Okay, so that means this sum should be 20. So in one case, the closing price was 37, and there were two cases where the closing price is 38, and etc. Okay, and for example, we experience 45 times. Okay, let's find the standard deviation here. So these are the closing prices, and these are the corresponding frequencies. See, there are 20 frequencies here. Now, first of all, we are gonna multiply them, okay? Because we have 137, we have 38s, etc. So when we multiply them, and divide by 20, guys, so this sum here, this sum is 800, and if we divide it by the total number of frequencies, we are gonna find 40. So that means the mean for this data set is 40. Now, based on that mean, let's compute the deviations first. For 37, for example, deviation is -3. For 41, deviation is 1. Then we square them, and we multiply by the corresponding frequency. Okay, we take this result, 9 times 1 is this 9 here, okay, and 2 times 9 times 1 is here 9, 4 times 2 is 8 here, okay. So then we are gonna take this squared deviations multiplied by frequency, and the result is gonna be 5 when we divide by 40. Okay, so for this data set, guys, so here first of all find the sum, divide by 2, 4, divide by 6, the result is going to be 5. Okay, so how do we interpret this standard deviation? Let's go back to, actually we can look at here. So the mean is 4D, guys, and the 5 is our standard deviation. So see, again, we can see, 5 is a relatively small number comparing to 4D. What this means is, for that company, the closing prices are kind of stable. Okay, it's stable because 5 is a relatively small number comparing to 40. For example, if we were to find, let's say, 30, so 30 is a big number comparing to 40. In that case, we would interpret as follows. We would say, well, since the standard deviation is 30, for this company the closing prices are not that much stable, so probably we don't want to invest in that company. Okay, so that's the interpretation. Okay, so the last one is, guys, the coefficient of variation. Here's the motivation. Now let's say we are given standard distributions of two different data sets. For example, let's say two different groups, okay, about their weights. So let's say, for example, in the first group, call it group 1, the standard deviation is 3 pound, okay, and for group 2 it's 10 pound. Okay, so can we say that the group 1 is more uniform in terms of weight? So remember the interpretation of standard deviation. If it's small, okay, we said if it is small, then we say the data set in that data points in that data set should be kind of uniform. Okay, so they should be kind of close to each other. But now, what do you think about this? What do you think about? We have two groups, and in the first group, standard deviation is 3 pound, and in the second group, standard deviation is 10 pounds. Okay, let's think about it. So, let me give you another information about these groups. So assume that the first group, in the first group we have preschool children, but in the second group we have NFL players. Okay, so these are big guys, we know that. Okay, so then see, just looking at these two information, it seems that if we have preschool children in the first group, guys, in the first group, it seems that the 9 pound here, 9 pound here, doesn't create that much difference, right? It seems that the second group is uniform in terms of weight, not the first group. Okay, so let's compare them. So it's clear that the 3 pounds is more significant for a group of preschool children, okay, preschoolers, and assume that the mean weight is given 30 pounds. Okay, so this is probably a statistical measurement. Okay, so the mean weight for preschool children is 30 pound. Okay, so then comparing to 3 with 30, it seems like 3 is more significant, because in the second case, guys, in the second case, the mean weight of NFL players is 300 pounds. So 9 is very, very small number comparing to 300 pounds. Okay, so with this example, guys, actually this example leads us to this definition, what we call coefficient of variation. Okay, so the idea is just standard deviation, again, just standard deviation, is not sufficient to correctly interpret the given data set. Okay, so how do we do that? So the idea is very easy, just divide by mean. All right, once we have the standard deviation, divide it by the mean. Okay, so we multiply by 100% to get a measurement in terms of percentage. Okay, so here's the example. For the previous case, guys, for preschoolers, the standard deviation was 3 and the mean was 30. Okay, so if we apply this formula here, so the coefficient of variation for children is gonna be just 10%. Okay, so that means there is 10% variation in that data in preschool children. But for the players, it's just 3.3%. See, so that means the variation in the preschoolers is more significant comparing to the NFL players. Okay, so that's the idea. Now, here's the last example for this section. So we have two companies, so you know these companies, Facebook and Twitter, and these are the closing stock prices when it is the first 6 months of 2016. Okay, so here are the January, February, first 6 months, and these are the closing prices for Facebook and Twitter. Okay, now let's find the coefficient of the variation here and then see how we can interpret that. Okay, so making a similar chart, we are not gonna do it again, guys. We can find the mean for Facebook is 114 and the standard deviation is 4, and similarly for Twitter we have 16 and standard deviation is 1. Okay, so the coefficient of variation for Facebook is 4%, but for Twitter it's 8%. So how do we interpret that? So we can see that there was more variability for Twitter than Facebook. That means, relatively speaking, that small phrase is important, guys. Relatively speaking, the closing stock prices for Facebook were more stable than Twitter. Okay, more stable. That means it's not fluctuating that much. Okay, so that's the whole idea. All right, so this is the end of this section, guys. In the next section, we are gonna talk about normal distribution, which is another important topic in statistics. Okay, thank you so much, guys. I'll see you later.